Written in this theorem says that if we have a limit of a function x go to c and then we put that x here, the limit is L. If we have a sequence that every term with real natural number inputs is not equal to that limit c to which this x goes in order for f of x to be at limit L. But then at infinity the sequence xn goes to c. If we put the sequence inside the argument of the function, then we have the limit L by that. So these two things should be equivalent. So we can prove the implication of this towards this and this towards this. So A towards B is this one towards this one as an implication. Well, I can let's take a real epsilon higher than 0, and we find then my limit definitions delta a real number higher than 0, and that will be such that for every x inside the open neighborhood of C bounded by the delta, we will have f of x will be inside the open neighborhood. So this is the neighborhood, the inclusive neighborhood that includes the middle point of the limit value of the function bounded by epsilon. All right. This is for the x-axis. This is for the y-axis outputs. And we also have that limit of xn as n goes to infinity should be c. And so we can find there will exist some natural number, capital case N, such that for every lowercase natural number, which this lowercase starts from this capital case N and goes higher than that, we have xn will belong, and also for individual natural numbers, not at infinity, but individual natural numbers inputs, we have that xn should not equal to c. So, by the way, this is a question of notation, but P and B both in neighborhoods. This one around L by epsilon, this one around C by delta. But the P means exclude C, while B would mean don't exclude the middle point around which we have the neighborhood. So in this context, if xn should not, for natural number inputs, is not C, well, we will put it not in the B neighborhood, but in the P neighborhood. So xn is in the neighborhood of C by delta. Alright, delta define the neighborhood for the x-axis. But then, by this, we then have that for every that lowercase n that is the capital case n natural number and higher, also the f of x n should be actually in the y-axis neighborhood, the one that is the limit value of the function by epsilon. And so this just directly leads to that thing that the statement B says, that limit, if we put infinity into the sequence and then put it as an argument of the function, we do get that limit value L. And then so this is the implication from left to right, A to B. For the implication from B to A, what we can do is actually a little bit different thing. That is, namely, we can instead do a negation of A implying negation of B. It's equivalent to proving that B implies A. And with that, how can we now deal with this? Well, let's negate this one. So this one says that we have, just like before, epsilon and higher, then there exists a delta. There exists actually an epsilon. And for every delta higher than 0, we have that x being in the neighborhood of C bounded by delta implies, but if it was not negated, it would simply imply that f of x is in the neighborhood of the limit value by epsilon, but we want to negate it. So we can either say like this, or alternative way is this means that f of x minus L, the limit value, under the limit of f of x, is more than epsilon. But if you want to negate it, we can say the following. We're negating statement A. So f of x minus epsilon, the difference should be higher or equal than epsilon. That could be a negation for that. Now for every n, so for every n in natural numbers, we find xn inside the neighborhood around the point C, but bounded by some number 1 over n, such that this is actually true. So we have a big distance between, or some minimal distance, but bigger than that even, possibly, between the limit value and what f of x is. But that's a problem. We also have, of course, we have xn is not equal to c, and we have lim of xn equaling c as n goes to infinity. But if this is not smaller than epsilon, then it's not true that n going to infinity limit of f of xn would equal L. It's not true. We have f of x minus L in absolute value higher or equal than epsilon. So this concludes the other implication, and the equivalence is proven from both sides.